21st century solutions for the benefit and betterment of mankind and the environment. The precious metal fragmentation and extraction system and plant, the ultimate 21st century solution to the mining of precious metals and recycling. In this laboratory model, hard, brittle material is exposed to high electronic resistors to accomplish electromagnetic fragmentation. Even the hardest material can be fragmented into granules of various sizes, right down to fine powder. An important advantage of this process is the complete lack of adulteration of the basic components of any material, which usually takes place in classical grinding processes. In order to achieve electrodynamic fragmentation, an extremely short electrical burst of 250,000 volts at 6,000 amps is required at a pulse duration of 200 nanoseconds, which equals to less than 1/1,000,000th of a second. And the power required to achieve this is an extremely economical rate of only 7.5 kilowatt hours of energy to operate the equipment. A water bath is employed as a conductor of the high-tension discharge onto the designated material. It is important to note here that different materials offer different resistances to different levels of applications of voltage and pulse durations. It is a fact that water offers only minor resistance to an electrical current. This picture changes drastically with the application of a high-voltage electrical burst at a pulse of less than 500 nanoseconds. At this rate, water offers greater resistance than most classic insulators, such as ceramics. In this system of electrodynamic fragmentation, a typical pulse duration of 200 nanoseconds discharged inside the water will affect the submerged solid materials to a greater extent than the water itself. The duration of the pulse used, however, is varied in accordance with the type of material. The destruction of solid materials by way of a high-voltage discharge can be separated into two categories. Depending on the duration of the pulse, we can achieve fragmentation through explosion, in which pulses are less than 500 nanoseconds, or fragmentation through compression with pulse durations in excess of 500 nanoseconds. This graph shows that air has very little resistance to high-voltage electric transmission. We therefore use water as the surrounding medium, since it offers sufficient resistance in the required range of extremely short pulses. Laboratory experiments utilizing different media of either water or air indicates that the combination of water and very short pulses achieve the best results. In the case of fragmentation of solid matter through compressive destruction, a great part of the generated energy does not even reach the interior of the material. This is caused by the diminution effect of the surrounding medium and the reflection or deflection of a considerable amount of energy from the surface of the solid matter. In the case of fragmentation through explosive destruction, practically all available energy is deposited in the solid matter. Through the application of extremely short and highly intensive energy bursts, the solid matter becomes the primary recipient of very high energy peaks. If the matter is brittle, it will fragment through the generation of induced internal forces. This results in the clean separation of different materials into their basic compounds or elements, making them available for the recycling process. This is equally true in the recovery of metals from an ore body. A very interesting application of the process is the fragmentation of silicates and crystals, i.e. rock formations containing precious metals. The very same process can be used for the removal of remnants of brake pads from brake shoes, the separation of metal parts from incandescent and fluorescent light fixtures, the total recycling of concrete, as well as the dismantling of electronic equipment waste. Hard materials such as minerals, ceramics, glass, and even pure silicone, as used in the semiconductor industry, can be recycled. Most impressive is the fragmentation of granite, spark plugs, and electric appliances into their basic components. The design of this electrodynamic fragmentation plant lends itself to the recovery of precious metals from silicone and crystals by the way of short-term induced magnetization of the metals and their sorting and separation process by means of an electromagnetic extraction system. A typical plant can process 2 tons per hour of black sand, which contains precious metals. The first part of the system consists of an electrodynamic fragmentation wavehead which frees the precious metals from the ore body and separates them into separate components. In the second part, the content is dried with hot air, thus blowing out and eliminating as much of the non-metals as possible. At this stage, the powder-like material is charged electromagnetically at a high voltage to induce an electromagnetic charge for a short period of time. Differing electrical charges and the varying levels of electromagnetic retention capacities of different metals make it possible to sort and separate extremely accurately precious metals from other matter. This machine will yield the maximum amount of precious metals without chemicals for the use of a high-temperature smelter. The precious metals extracted through this method are pure and raw, making it possible to recover the maximum amount of content without chemical alteration or the danger of evaporation caused by a high-temperature smelter. In short, this process opens a new chapter in the history of gold and precious metal production. A patent for this plant and process has been applied for by Dr. Hisabi and is being developed in Nevada.